Okay, so last time we talked about the subthreshold conduction. I want to go over quickly a little bit because this is something very important in this class. And so what is subthreshold conduction? The main point I show you here was that this is a transistor. And you should know that all the conduction occurs at the surface. Of course, later when we talk about FinFET and 3D device, the conduction can conduct at the middle, which we call it the volume inversion. But for now, we just look at this, a planar CMOS, right? It conducts at the top. We draw the band diagram, right? The band diagram, the most important thing is to realize that a band diagram is the energy plot against the position. So when you go up, this is the energy. But energy of electron, that is the main point. Think about the energy of an electron. Electron has a higher energy when it is under negative potential. Okay, it's not a positive charge. If it's positive charge, then it has a higher energy at higher potential. So as a result, if at the source I put 0 volts, at the drain I put 1 volt, the drain band, the part of the drain is going to be lower because it has lower energy, right? Because an electron has a lower energy at the higher potential, which makes sense. Lower energy means more stable, and your electron is attracted to a high potential, right? So it's difficult to remove it, so it's more stable. And the gate, for the gate region, it goes up because of many things, including so-called gate work function, etc. But one important thing is the gate bias, the gate voltage. We start from 0, or just think of it as negative. This is the red line. We make it very high. So as a result, your electron cannot go through this barrier. Right? This is very classical. Right? It's just like you have a wall, right? Or think about you have the mountain and your electron is at the valley. Right, so in the mountain case is that you are talking about potential energy or gravitational potential energy, right? That you are at low energy, you want to go over this mountain, you need to gain a lot of energy to go over. Here we are talking about the electrostatic potential energy, right? So electron here has a lower energy compared to electron here, so you need to go through this barrier. So this is pretty intuitive, right? Now, but remember that electron follow the so-called Fermi-Dirac distribution, right? If you forgot this, this is Fermi-Dirac, right? Both are important guys, right? Guru, right? Distribution is telling you that, again, this is the vertical plot is a plot of energy, E. Here, the horizontal plot is the occupation probability. Basically just saying that if I have a very low energy, at the very low energy regime, the electron will occupy all the state, which makes sense, just like the dust I told you earlier, right? The truck drive through and then you have a lot of dust on the floor. But if you want to find the dust that has very high energy, means they go to 10 floor, it becomes much less. Of course, that is Boltzmann distribution, not Fermi-Dirac, but just think in this way. The point is when you go up, you have exponentially less electron with higher energy, right? So in principle, I still have some electrons. So it's not all electrons sitting here due to this Fermi-Dirac distribution and due to the finite temperature, okay? So some electron has pretty high energy. Of course, they can transport through this barrier and go to the drain. As a result, you have a current, right? And that's why when I plot this IDVG curve, I start with 1 nanoampere. I put it in a log scale, Ln log scale. So this is 1 nanoampere, and then maybe 1 microampere, and then 1 milliampere with equal spacing. I put it in a log scale, right? So when it is 0 volt, I only have very tiny electrons, a very small amount of electrons that go through, so I have a small amount of current. But if I increase the gate voltage to 0.5 volts, again, positive, right? More positives, it means that this barrier will be smaller, right? Because, again, this is energy of electron. Then I get exponentially more electron that has energy that can go over this barrier. Because this increases exponentially, right? My drawing does not show that, but it is an exponential function at this tail. And that's why the current goes up exponentially, right? And then I remind you that if you plot this in the linear scale, you will just go back to what you learned in the more fundamental circuit or device class, in which that we say, okay, before the threshold voltage, you have zero current. But in reality, it is not. It's just because we're plotting in linear scale, we care about on current. We have 1 milliampere, 2 milliampere, 3 milliampere. If you have 1 microampere, 1 nanoampere, is 1,000th or even 1 million, 1 billionth of this scale, then when you look at it, it's like zero. Make sense? And last time we have someone say that, hey, this one looked like a diode. And I remind you that, yes, indeed, this is just a diode, except that this time the diode at this side is controlled by the gate full capacitive coupling. Okay, and then we also have a drain. So that is the first thing. Any questions? Yeah. Increase go up. We're talking about the electron energy. This is
charges at the bottom, according to the problem portion, then you have it on top, right?
no. This is just talking about the probability of occupying that state. It is not talking about how much charge you have. So this probability then multiply the available state, right? The density of states. So basically, it's just like a building. In the building, you can say, for example, me, right? I can jump, let's say I can jump pretty high, right? I can say I have this probability of occupying the first floor, this less probability to occupy on the second floor. But the point may be on the first floor, there's no room for me. So even I have probability to occupy because I can jump that high, but actually I cannot occupy any room. So the final electron concentration depends on this function, the probability times the density of state, the amount, how many room that you have. Okay, that is one thing. But I feel that you probably still also thinking about saying that you say you have more electron occupied, so the energy will go down. So not really, because remember there's a background charge. Here we assume charge neutrality. So no matter how many electrons you have here, I have the corresponding amount of ion, positive ion. So there is no net charge here. Yeah. Okay. So then we talk about the subthreshold conduction. I have all the number for you. The most important thing we want to learn from here is the subthreshold swing. It tells us how fast I can turn on and turn off a transistor. It's saying that in order to change the current by 1 decade means 10 times. Okay, so let me remind you, 1 decade means 10x. Okay, in order to increase the current by 10 times in the subthreshold region, right? How much voltage I need to change? For example, ideally, I want to have, maybe we start with this. For example, for 300 Kelvin, in order to change 10 times, usually it's about 60 millivolt per decade. And this is mandated by the physics, which we already talked about this, because when I increase this by 60 millivolt, the amount of extra charge you can go through is increased by 10 times. You just go through the physics, you will see that, but we won't discuss this, right? So if I go to lower temp, and then this is the equation, S equal to nkt over Q times log 10. If I go to lower temperature, let's say 3 Kelvin, then I can increase it even faster, because now the distribution is even more steep. They change a lot. Okay, now, so last time I did not have the chance to talk about this N, so maybe I should take this opportunity to talk about this. So what is N? It is like this. I have a transistor here. And then here I have the oxide, right? This is the oxide. And this is the gate. So when we talk about subthreshold slope, of course, we're saying that now, if I can reduce this by 60 millivolt, right, the barrier, then I would have 10x more current that can go through. But as we said, this is not a diode. We do not touch it directly. We did this through capacitive coupling. What really happening is this. We actually go through this capacitor to the surface of the transistor. And then remember, we do have a depletion layer. This depletion layer then connected to the ground. So actually there are two capacitors. And what we're trying to change is this voltage, which I will call Vx. Okay? So what is Vx? Then you can go through the potential divider equation. I usually will think it in this way. Vx equals to Vg, right, times the impedance of, if this is CD, this is Cox, then it is like this. Just a potential divider or resistive divider, right? Because it's capacitor. So remember the impedance of capacitance is 1 over omega C. Right? That's the way I memorize it. So this is like the resistance of this, the impedance of the bottom part. So it is how much resistance you have here divided by how much the total resistor in this series, right? Do you see what I'm talking about? Any questions?
What is CD?
What is what?
What is CD?
CD is the depletion capacitance. You remember when you do a transistor has a depletion layer?
Is that
The immobile charge, right? So that is insulating, so it becomes an insulator, and then you couple from the channel to the substrate. Yeah. So let me. Getting more messy now, right? Let me. But this is good to make it clear. Let me have another. Let me have another thing to make this clear. If I have a voltage here, and then I go through this resistor, and I want to find what is the voltage here, and this is grounded. This is R O, this is R D, for example, right? What is Vx? Vx equal to Vg times Rd divided by Rd plus Ro. Let me call it Ox, otherwise it's difficult to see. Are you okay with this equation? Yeah, just a resistor divider, right? Vx at this point is just Rd divided by Rd plus Rox times Vg, right? And you can do similar thing for AC, but or you go through all the equation. You can memorize in this way because 1 over capacitor is like the impedance, right? So now it's 1 over D divided by this guy. The sum of these two resistors, impedance. Okay, so the main point here is that then it means that this equal to Vg times Vox, not Cox, divided by Cox plus CD. Okay, let me remove this 1 that k equal to 10x. I think you guys know that now, right? Then what does it mean? It means what you have here, Vx or Vg divided by Vx is equal to Cox plus CD divided by Cox, which is equal to 1 plus CD divided by Cox. And this is what we call the N, the non-ideality factor in this case. That's what I have here. So you see that it's always larger than 1, which is not good, right? Because we say that we want to have a small subthreshold swing. We want the n to be small. But now it's always larger than 1. So can you tell me how I can improve the swing, subthreshold swing, by changing CD and COX? Do you want to have a large CD or a small CD? Small, right? The best is CD is very tiny and or COX is very large. And that is one reason we want to scale the transistor so that you have very thin gate oxide. When you have a thin gate oxide, you have much larger COX. That improves the subthreshold swing. Now theoretically, KT over Q times log 10 gives you 60 millivolt. But depends on the quality of your transistor, right? The COX and CD, your N will be larger than 1. And so that's why usually it is larger than 60 millivolt per decade. It can be 65, 70, but that is a comparison. If you read paper, people will say, now we have this nanosheet, 3 nanometer technology, and we still can achieve a subthreshold swing of 67 millivolt per decade, which is pretty good, right? Because if you go to 90 nanometer or 65 nanometer, it's very easy. You will touch maybe 70 millivolt or 80 millivolt per decade. Right? It means I need to swing more in order to turn off the current. Okay. Any questions? If no, then last in the very end of the last class, right? On the left, we say why we want to have a steeper subthreshold slope. We can have a better N, right? Or lower temperature. Because for the same on current, I will have a lower off current, right? This is I off. This curve has the same amount of ion as this one, but it has a large off current. This is a log scale again. So this is talking about at least 10 times, 100 times, or even 1,000 times more leakage than this device. Okay? And the total power consumption of your chip depends on the switching energy. This is the switching. So you turn on and turn off your transistor when you do the logical calculation, right? So this is something you almost cannot avoid. You can reduce it by reducing the capacitance, reduce the VDD, reduce the switching frequency. But there's another part, which is the leakage current, I off times VDD. Now, if you have a very large I off, this can become very dominating. Okay. Now, that is one thing. But, as I said, we have abnormal subthreshold slope. So based on the equation, again, what is the equation for the subthreshold slope? We expect such subthreshold swing, or sometimes we say subthreshold slope, is N times KT over Q natural log 10, okay? Natural log 10. So it should scale linearly with T. So if the T goes from 300 to 3 Kelvin, I expect this improved by 100 times. If you go to 0 Kelvin, absolute 0, I expect that I have an ideal switch. I can turn it on and off vertically, like this, right? But no, all the experiments are very interesting. Whether you are about PMOS, FD-SOI, we will discuss later, fully depleted SOI, silicon on insulator, silicon germanium nanowire, or P-type FinFET, they all exhibit a saturation of the subthreshold slope. Okay, and why is that? Although recently there's a paper saying that there's a saturation, but when they go to millikelvin, they see it dropping again. But there's no one knows what exactly what's going on. Very novel. But anyway, this is very universal, right? I also did the experiment in my lab. We see the same thing, right? So very universal. So why is that? So there are a few theories, right? Here I just want you to know about this. You might not deal with that in the future, but if you need to deal with that, then you know where to look for. One is the so-called band tail theory. What does it mean? So again, you are familiar with what I draw, what is drawn here. This is the band diagram I drawn earlier, remember? I have a cut line along this top channel, and then we draw this band diagram. So same here, here we have the source. This is the drain. Here is the conduction band. Here is the valence band. And EI is just the intrinsic level, energy, Fermi level, or just the middle of the band. Just think about the middle of the band, which doesn't matter. What is the meaning of band theory, actually? It is a calculation of infinite atom, array of atom. You go through all the math, and it tells you that under some condition, in certain energy range, you do not have any density of state. And basically what it's telling you is this. Maybe you have a building. I think you have seen many of such buildings before. You have lots of room at different level, from first floor to 9th floor, and then from 11th floor to 34th. But somehow on the 10th and 10th floor, you don't have room. They just put it as maybe a podium for everyone, right? Or for the ventilation. Have you saw this skyscraper before? They don't have room everywhere. So basically, this is like this. You have a region that you cannot put any electron, or you don't have electron that an electron cannot obtain or cannot process that amount of energy at this level. The electron can have a higher energy or a lower energy, but you cannot find an electron with this amount of energy, right? And that is called band gap, right? Which you learn in your solid state physics or derived physics, but here I just repeat again, what is band gap? Band gap is the energy region in which you cannot find any electron. Right? But again, this is the energy space, so it's not that you cannot find. It means that no electron can have this amount of energy. Make sense? Okay. But this is only true when you have an infinite crystal. In reality, our crystal is finite. Then you are not going, and then you don't have this very sharp edge. I should mention this is called band edge. On top, I have a lot of state. Above the conduction band. Below the conduction band, I have no state. And it's very sharp. You cannot say I'm 10 millivolt close to the conduction band, so can you give me a state? No, for infinite ideal crystal, you cannot. But however, in reality, a few reasons can cause some states there, and that is the so-called band tail state, right? So I would say that there are a few reasons due to maybe, of course, our crystal is finite. So it won't be infinitely sharp, right? Second, you might have defect. When we calculate the band structure, we assume perfect silicon, right? So they might not be perfect, right? The third thing is you are at the interface between the silicon dioxide and the silicon. So it has an abrupt change. Definitely that is not the ideal condition that we have, right? So the final message is that I do have some states right at the edge. It's not abruptly sharp going from with state to no state. Is that okay? And here shows that you might have some tail with some characteristic length of 1 milli eV or 5 milli eV. Indeed, they are very sharp. 1 milli eV, talking about 1/1000 volt. So the band gap of silicon is about 1.1 eV. Then it means that these they are only within maybe 0.1 or 0.5% of the gap. Now, if it is at room temperature, you won't feel it. But when it is at the cryogenic temperature, this becomes a large scale, right? So then, as a result, because of this band tail state, you can have the what they call band tail current here. It can due to hopping or other mechanism. Hopping means that you have a lot of defect. So your electron can jump from one defect to another defect. And of course, quantum mechanically, this is just tunneling. Now your defect is so close to each other, I tunnel from one defect to another defect. And this completely changed the mechanism because this transport is due to the limitation of the Boltzmann statistic. And we assuming that this is abruptly sharp, so there's no current in the band gap, right? But because of that band tail, you have that. And as a result, when you go to very low temperature, you cannot get an ideal subthreshold swing. Now this paper, right, this group has derived quite some equation, but I never really try to follow because it's pretty complicated, but they can match the result. Yeah, so that is a possible explanation. I did not follow too much, but whether this is completely right, no one can say for sure because you really need some physical measurement or proof from another way, right? For example, there's another theory. This theory is talking about the trap. You might have some trap between the oxide and the band gap. So this is a diagram that got rotated. Here is the conduction band, and here is the valence band, and here is the band gap. Right. So some people suggested this can be traps. Now you cannot reproduce the experimental result by uniform trap because the author from the last paper proved that, right? But however, can non-uniform trap produce that, right? I will show you some of our work. And another thing is that it correlates to the 1/F noise in some paper. But again, this is not convincing yet, right? You can try to take a look why the trap has an effect. But I want to say this, why the trap has effect is because of this. When you have a oxide here, right? And again, this is N plus, this is N plus. Now again, I have a COX, and from COX to the bottom, I have the C depression, right? And remember that our electron here, this is the electron, right? So that as a result, we care about the potential here, which is Vx, and this is Vg, right? That's what we just discussed. Now, if you have the interface trap, it acts as you have one more layer of capacitor, which is CDIT. DIT is just the interface trap, right? So we do not have time to go to that, right? I do have some video that you can take a look if you're interested or ask me. But otherwise, just take it for granted. When you have some trap, some defects at this interface, equivalently, you have more capacitance at the bottom. And then because of this, what is N? Okay, so N will become 1 plus CD plus CDIT divided, sorry, I don't want to call it DIT, just call it IT. That's what I had. Right, and then divided by CD plus CIT plus COX. Now, if you compare this to the previous equation, the only thing we have the only difference is that we have CIT. Now, let's go back to the previous equation. I try to derive to you. You got COX plus CD divided by COX, right? And what you have now is a parallel CIT next to it. So you can just substitute CD by CD plus CIT. Now, with this one, then it means that even I don't have depletion capacitance, I still have a very large CIT, right? So this increases the N. And in increase the N, then it can increase the subthreshold swing. Now, but it's not that simple, of course. Just have a feeling, right? Otherwise, you would say this one looks like to be constant. but CIT depends on the level of the Fermi level, okay? But no, we don't go into detail, right? Just pay attention to this. Now, indeed, we did some simulation, right? This is done by our student, right? So what we did is we found some experiments with our collaborator at that time. Is that our collaborator? Yeah. Actually, I forgot where this data come from. Need to read the paper again, right? Might not be the one from our collaborator. But what we did is we tried to have a variable instead of uniform traps density as a function of, this is actually a conduction band edge. This is conduction band edge. Okay, and this is the band gap. And you see that we have everything within about 50 millivolt, right, from the conduction band edge, this offset from conduction band edge. And if we try to do the simulation, which is our cross here, we find that we can match the curve that I showed you earlier pretty well, right? You also show a saturation of subthreshold slope, right? But now, you will see the band tail states and the trap actually is difficult to distinguish, right? Whether it's a band tail can also be a trap, right? What is the main difference? Here is that you only change the electrostatic potential when we use this interface trap theory. You just make it more difficult to turn it on. But here is that they assume there's a conduction. The current go through this band tail state. So it also changed the current, right? But the result is that we can match similarly. But of course, then what if we go to other gate oxide thickness? We have not tried, but looks like it will be difficult if we go to even thinner because we need to have a very high trap density. This is a cm squared per EV. It becomes maybe too high, right? So again, I don't know if our theory is correct. Okay, so it's done. That's all I want to talk about the subthreshold slope. Any questions? Now, if you forget everything, I don't mind. But you definitely should remember that the subthreshold, what is subthreshold swing? And remember that it's saturate. Remember that it can have some theory, band tail and trap, but the main point is that due to the long ideality of the band tail. Okay, and then remember, memorize this equation and understand the effect of depression. That's what I need from you, right? These are too much if you want to understand the theory. Okay, yeah. Or interface? It is the interface between, again, right? The current transport on the surface of the silicon. So it's the interface between the oxide and the silicon. The insulator and the silicon. Okay, good. Okay, so then we are done with this. Then now we want to talk